The following program is part of Cable in the Classroom, a service of the cable television industry and your local cable company.
You're not going to need this for the next 30 minutes.
Second law of thermodynamics?
What was the first law?
I don't know. Hey, welcome to SportsFigures.
On ESPN2.
Where sports and science go one-on-one.
Where physics get physical.
Where math gets mathematical.
Where sports figure.
Go figure.
It's SportsFigures.
Jeez, where's this guy come from? Jeez.
A lot of racket is being made in the tennis world about the longer tennis racket.
The normal racket is 27 inches, and you could legally use a racket up to 32 inches. But as of 1997, the ITF has declared 29 inches the maximum length for pros.
So why all this racket about longer rackets? Is there really that big a difference? Well, let's join SportsFigures' Kevin Flynn and MaliVai Washington to serve up some answers.
So why would a tennis player use a longer racket? You see, it's all about power. A longer racket gives your shots more power. Sorry about that, kid. Wait a second, the standard tennis racket is 27 inches and the longer racket is 29 inches. That's a difference of 2 inches. 2 lousy inches, that's all they give you. I mean, how much more power is that gonna give us? And how are we gonna figure it out? Wow, this is MaliVai Washington. 1996 U.S. Olympic team member, and in '96 he won the Bermuda Open, and he was a finalist in Wimbledon. So this guy definitely knows about tennis rackets. Hey Mal, how you doing?
Good, can't you see I have a match here?
Oh yeah, I know. I just want to ask you one quick question though.
Okay.
What can you tell me about racket speed?
Well, racket head speed. Most players want to get as much power on their shots as they can, so what they want to do, they really want to get the racket head through the ball as fast as they can. That's where all your power is going to come from.
So what kind of tennis racket do you use?
I use the Yonex RD7, just a standard 27-inch racket.
Oh, have you ever used a longer racket?
No, but can I get back to my match now?
Ooh, yeah. Sorry, Mal. Go get him.
Okay, thanks.
First, let's take a look at why a longer racket means more power. Well, when you're talking about power, you're really talking about force. How much force the racket exerts on the ball. Okay, kids, so how can we figure out how a longer racket can give us more force? Okay, we can start out by drawing a triangle. Hey Mal, what can you tell me about a triangle?
Well, a triangle is a plane figure formed by 3 segments joining 3 non-collinear points.
He's absolutely right. 3 segments joined by 3 non-collinear points.
And non-collinear is just a fancy way of saying the points aren't on the same line.
That's right. If they were in the same line,
Well, then we wouldn't have a triangle.
we'd have...
We'd have a straight line. Hey, I gotta get back to work.
Go get him. So, we need a triangle to figure out why a longer racket will give us more force.
Okay, so where's this triangle you're talking about?
All right, pretend you're hitting. There it is right there.
Where?
Well, when you're hitting, the racket makes the triangle. Check it out.
When a racket hits a tennis ball, the movement of the racket forms a triangle. One segment is the racket's position when we start to swing, and one segment is the racket's position when we hit the ball.
Hey, Mel, what can you tell me about the sweet spot?
Well, the sweet spot, it's in the center of the racket, and that's where obviously you want to hit all of your shots. That's where your power comes from. And when we're talking about racket head speed, it's the speed of the sweet spot that really matters.
Oh.
Okay, Kevin, do you mind?
Oh, yeah.
Thanks.
So it's the path of the sweet spot that will give us the third leg to our triangle like this. This angle here, let's call it theta, is our swing. We can say that's how much effort we use to hit the ball.
So now that we have our triangle, what happens to the triangle of the longer racket?
Well, the third leg gets longer.
If the longer racket makes this leg of the triangle longer and this leg of the triangle longer, then the path of the sweet spot is longer too. But notice that our angle, theta, hasn't changed at all.
The whole reason why a longer racket will give you more force rests in the amount of distance that the sweet spot has to travel.
The sweet spot travels a longer distance, but in the same amount of time.
Must be going faster.
Right, exactly. See, you're swinging the same speed, and the angle doesn't change, but you're getting more speed. And the more speed, the more force, and the more force... More force means I couldn't possibly return that. Hey, take it easy, will you? So we know that a longer racket gives us more force, but how much more force does 2 inches longer give us? I mean, 2 inches is nothing, right? So Mal, how are we gonna figure this out?
Well, I think it's gonna have something to do with triangles.
But of course.
So we've created 2 triangles, right? One using the long racket and one using the short racket. They share the same angle here, theta, right? And they also have equal angles out there. They have to because the 2 sweet spots run parallel. So we've created 2 triangles with different sizes, even though the angles are the same. When 2 triangles have the same shape, but their size is different, they're called similar. It's like when you blow up a photograph. The original and the enlarged are similar because they have the same shape, but they're not equal because the size is different. What are you looking at?
The same is true for our triangles. One is just a blown-up version of the other. To denote similarity, we use a symbol that looks like this.
Now there are 2 conditions that must be met to prove that triangles are similar. First, the corresponding angles have to have the same degree of measure, and the length of corresponding sides are in proportion. Proportion? Lengths of corresponding sides are in proportion. What does that mean? We can take a look at proportions this way. For every 2 steps I take, Dana takes 3. I take 2 steps, Dana takes 3. I take 2 more, Dana takes 3. See that Dana's traveling farther than I am, but her movements are proportional to mine.
3 to 2.
And what do we call this?
A ratio.
Ratio, right. Ratio is how we describe proportion. For every 2 steps I take, Dana takes 3. Now using this, we can figure out how far Dana goes if I took 10 steps.
15 steps.
Simple, right?
Yeah.
Yeah, it's simple.
Simple.
Yeah, it's simple.
The sides of the triangle have to be in proportion, and the angles equal for 2 triangles to be similar.
Wait a second. If we have 2 triangles and 2 of their angles are equal, the third would have to be equal because they have to add up to 180 degrees.
Right. And the lengths of the corresponding sides must be in proportion. If they weren't, the angles would be different.
So all you really need to know is that if 2 angles are equal, then the triangles are similar.
Exactly. If the triangles are similar, they're proportional.
Excellent.
Excellent. So where is all this going? We're going to use similar triangles to figure out how much force we get. Check it out.
So we know that our 2 triangles are similar, and we can easily measure the length of the racket to the sweet spot. For the shorter racket, it's 21 inches. For the longer, it's 23 inches. We don't know the distance the sweet spot travels, but we don't need to. We know it's going to be in proportion to the sides. These 2 triangles form a ratio. You can kind of think of it like this.
If we create a ratio using the different lengths of rackets, we get
23 to 21 inches long.
right, 23 to 21. Or we can write it like this.
Or we can turn it into a decimal by dividing 21 into 23. The ratio of our two triangles is 1.10. So we know that the two sides that represent the path of the sweet spot are also in a proportion of 1.10. That means that for every 1 the sweet spot travels on the shorter racket, the sweet spot of the longer racket travels 1.10.
And if it travels 1 1/10 further in the same amount of time, that means it's 1 1/10 faster. So 0.10 means the racket head gets moving 10% faster. That's 10% more power in a shot with a racket with 2 more inches.
Wow, that sounds great. Can I borrow that?
Sure.
Thanks.
Two-hander. Ooh, there's a beauty. Oh, Kevin Flynn model racket. Ooh, that's a bird. I was in.
So 2 little inches give us 10% more power. Woo. And we figured it out using triangle similarity. Pretty cool, huh? So now, if you get 10% more power from a longer racket, how come everybody's not using one of them?
Well, if you get 10% more power, you're also going to be sacrificing 10% in control. Everyone has to understand that that 10% is going to be affected with every movement you have with your racket. If you have real good power, you may want a little more control, but if you have good control and want more power, you might want to go to a longer racket.
Why would anybody want to know this stuff? Well, you can use it for more than just figuring out a tennis racket. I mean, there are millions of ways to use similarity. Anybody who uses plans or blueprints, like a landscape architect, I mean, they use similarity every single day. I'd like to thank MaliVai Washington, the students, and the ATP Center for helping us out with the Racket.
Out!
Out! Big on power, not much on control.
Thanks, Kevin. Now here's something you might want to figure out. Until 1997, a player can legally use a racket 32 inches long. How much more force would that give him or her, and why isn't anybody using a racket that long?
Sports Figures, explanation of the rules, the working of the universe, the research and its tools. Sports Figures, we take you up in the air, on the ice, in the field, gonna put you right there. Sports Figures, we got the players you know, with examples from the game, we help your mind to grow. Sports Figures is something fresh, not the same. Sports Figures, we put your brain on the game.
You get that last part?
I think so.
You forgot to carry the 2.
Hey, cut that out. Your own paper. Quit cheating.
That's it for today on ESPN2's Sports Figures.
Thanks for watching, and we'll see you next time.
On ESPN2, Sports Figures.
Doink. Well, guess we won't be needing this anymore.
We're done.
You want it back?
All right. You can have this back now. Thanks for watching. Go. It's over.
ESPN2 Sports Figures is presented commercial-free for educators to record and use. Curriculum guides are available to help integrate sports figures into your classroom. For more information, call your local cable system or Cable in the Classroom at 1-800-743-5355. You can also access Sports Figures lesson plans by connecting to the ESPN Net Sports Zone at the internet address on your screen. ESPN2 Sports Figures makes math and physics a ball.
The preceding program is part of Cable in the Classroom, a service of the cable television industry and your local cable company.